to show you how I acquire C13 with F19 decoupling. First thing I want to do is just make sure that the parameters are set right. So I'm going to switch the nucleus to just carbon-13 with proton decoupling. And the pulse widths and decoupler power should be about the same. So notice that the pulse width in the acquisition column is 15.3 microseconds, and in the decouple column the decoupler power is 36.2. So let's make sure that those are the values when we load the C13 F19 parameters. Load those from the pull down menu. Notice the pulse width is 15. I actually reduced it down to 15 instead of 15.3. Doesn't have much effect on the outcome. And the decoupler power is 36.2. I'm going to use a program called ACQF, which acquires carbon with fluorine decoupling. Give it a name. 1,4-dichlorobenzene is what I'm running right now. It'll automatically put the C13 1D on it, so I'll just leave that off. Do you want to shim? I'll just shim the Y shim. I'm going to change the parameters and tell it to do 128 scans. And I really don't know what the delay is from previous C13 F19 experiments. It didn't seem like a longer delay helped, but let's just change it to 6 anyways. And what data size do you want? Standard data size is 32K, so we'll just stay with that. And finally, what flip angle? So if you do a 90-degree flip angle, the maximum amount of magnetization is going to be transferred into the XY plane. But if you choose a 60-degree, about 87% of the net magnetization vector is transferred into the XY plane, and it relaxes a lot faster. And you can even do better with a 30-degree, but let's just do a 60-degree and see what happens. So this is going to adjust the gain for the F19 first. Notice that the first dimension is changed to F19, just so that it can shim and find out where the peaks are and whatnot. It's got CFCl3 set to 0. Right now it's asking me, where do you want O2 to be? And we should place it as close to the middle of the peak that we want to decouple. So I'm just going to click on that peak. And you'll see when it starts collecting C13 data that the O2 for the decouple channel should be around minus 67, 6800 hertz. There's our parameters on the screen. Notice our pulse width and decoupler power are set where they are. The O2 is changed to minus 6779. The nice thing about this program is while it's running, you can process the data. So it saves the data to the hard drive after every scan. Notice that, I'm just going to bring up the cross here quick, turn off auto scale. There's 2 peaks starting to appear in the spectrum, and I think those are the peaks for this molecule. We'll see in just a second. We'll acquire a few scans and then go and process it. I'm going to use the SNAP program for processing. We'll just do a file open up that file, and we're going to do some exponential multiplication. And just as a first go around, usually you want to match the natural line width. I'm just going to use 1 hertz. Do an EM command, exponential multiply. Gives it more of an FID look to it. We basically reduced all the noise on the right hand side of the spectrum. We'll do a Fourier transform, and I'm just going to use a DC command to bring it up off the baseline a little bit. We can see some peaks. I'm going to do a little manual phasing first, just so we can see these peaks. And it looks like there's 2 peaks coming in around 110 and 122 ppm. I don't know if those are real or if that's just noise. They look like they're real. This was the data after about 10 scans. Let's just take a look. 6 scans. I'm going to load the buffer with the AL command and DD, do a dual display, just so I can keep that on the screen and see what it looks like after I process the data again. And I'm going to do that. In the meantime, it has now acquired 16 scans, so we'll open up that file again. And we do BC, EM, FT, phase same. Notice that the signal is increasing rather dramatically, so it looks like not only do we have those peaks at 110 and 122, there's another peak coming in out here. And this is what you'd expect from 1,4-difluorobenzene. The carbons with fluorines directly attached will be decoupled, but the carbons right next to them will not be. They each have a proton attached, so they'll be split into a doublet, and there's 4 of those. Likewise, the protons near the CF atoms will be split by those nearby protons. So even though we're doing decoupling, that doesn't mean we're just going to get singlets and whatnot. So I'm guessing that the 2 tall peaks here are the 4 carbons that have protons attached. We're not decoupling protons, we're decoupling fluorines. And that this peak over here is the one with the fluorine attached, and it's coupled slightly to the hydrogens that are nearby. Let's load that into the buffer. Notice that the buffer now is a carbon copy of the lower one. I'm going to bring that back down a little bit. And let's go see how much data is collected. 28 scans. Let's open up the file, and we do BC, EM, FT, phase same. Peaks are getting bigger. So in a very short, oh, by the way, the concentration of this, I put in 500 microliters of 1,4-difluorobenzene, and I put in 250 microliters of CFCl3. So we're seeing data after a very short number of scans. We're going to let this go. There's 32 scans. Let's go ahead and grab that. BC, EM, FT, phase same. Yeah. So even after, so this is about a 66% solution. It's pretty concentrated in the atoms that we are looking at. So it's not surprising that we're seeing data this fast. We didn't need to set it up for 128 scans. So we'll go back to this program, and after this has collected a number of scans that are a factor of 4, so 40, I'm going to just kill it. You can kill it using the mouse with the kill command. Go and process that data. File open. BC, EM, FT, phase same. Get rid of the dual display. Set a minimum height threshold for peak picking. Let's zoom in on these just to see what they look like closer. Oh yeah, and we're still, even the ones that are fluorine decoupled, you see there's other small splittings that are splitting those into this other peak. So there is some interesting stuff here going on. I'm guessing that this is the fluorinated peaks and these are the protonated peaks over here. So that's it in a nutshell. Carbon with fluorine decoupling.